I'm Andrew Lahiff. I'm from the UK Atomic Energy Authority, and I'm going to be talking about a generic simulation monitoring framework. So just a quick overview. We'll begin with an introduction and sort of what the problem is that we're trying to solve. Talk about the system that we've developed, which is called SimView, and then sort of talk about a few example use cases as to sort of showing how we're using it, and then briefly give a summary and talk about future work. So obviously these days many people are running simulations, but people are sort of running more and more simulations. So people are like doing parameter sweeps, doing uncertainty quantification and things like that. So it's sort of becoming harder and harder for people to actually keep track of sort of everything that they're doing. And so just doing things manually with notebooks and things like that is sort of not really possible anymore. And then there are situations where people are sort of running lots of simulations where some of them might work, others might sort of, they might converge, others might not converge. So it'd be good to actually have some way of actually keeping, sort of monitoring, keeping track of what simulations are doing while they're actually running. So at the moment, so a number of codes, sort of both within Fusion community and sort of more general applications, people frequently use sort of GNU plot-based scripts. So they manually have to SSH into a machine, run some scripts which generates plots, and they then can sort of check the convergence and if their simulation's working well or not, which is sort of not really the best way of doing things these days. So in the world of, sort of artificial intelligence and machine learning, it's sort of becoming more and more common for people to make use of platforms that track and monitor their experiments while they're running, which I'll talk a bit in more detail next. But in the sort of HPC simulation world, this is sort of not really happening much. So it'd be sort of useful if that there was a sort of generic monitoring framework for monitoring simulations. So as I mentioned, I mean AI and machine learning, there's increasing number of companies that provide experiment tracking platforms. So these basically let you track experiments. So you can sort of input, they can collect like input parameters, information about versions of codes, metrics while the codes are running. Then it provides a dashboard that gives a sort of centralized view of everything, and you can search for things, do comparisons between different experiments, and sort of understand what you're doing. And obviously it also can collect artifacts, so for example, data sets, the output models, and provides the model registry so people can keep track of all of the different models that they're actually generating. And then after that, it then helps people actually monitoring their models in production when they're actually being used. So a lot of these surrounds, a lot of them are commercial, but there's also some open source as well. And then there's also distributed tracing platforms. So these are sort of used to monitor the performance of distributed systems. So for example, if you've got like a website or UI, REST API with like databases and queues and different processing things taking place, and you've got a latency problem or things not working, you can use distributed tracing to sort of understand the flow of data through the system and understand what's happening. So these things can sort of collect metrics, metadata and events and things like that, and then provide a dashboard. And they also can provide alerting, so you can sort of get alerts if things are not working. But sort of this covers sort of some of what we want to do, but not everything. So obviously this doesn't track data or sort of things like that. So we then were sort of looking at developing our own platform called SimView. So this is quite new. We've only been working on this sort of in the background over the last few months, so it's just a proof of concept. But we thought it was sort of good to sort of get feedback from people to sort of see how many people would be interested in this type of platform and what sorts of features they need. So there's sort of 6 main sort of areas that it covers at the moment. So there's tracking, so you can monitor and track any type of simulation and have a single dashboard to keep track of things, and you can obviously do queries and things like that. It collects metadata from simulations, and like tags. You can have a description, write notes as it's going and things like that if you need to. You can save any type of artifacts, whether it's software, input or output files, or intermediate files while the simulation is running. Collects time series metrics, so if you need to monitor the performance of a sort of long-running simulation, you can then sort of watch that in real time and sort of see what's happening. If you can then collect events, so for example, it could be like exceptions, or you could collect errors or sort of log messages from log files, and then be able to search for different keywords. And then, so if something's going wrong, you can sort of find out about it. And then sort of making use of both of the metrics and events as alerting, so you can set up rules based on metrics or events. So for example, if a metric goes above or below a threshold or outside of a region, or if a log file contains some particular error message, you can then, that particular simulation run is marked with an error, or you can get like email notification or whatever. So that sort of helps you to automatically find out when simulations are not performing well. So the current architecture is mostly based on ArangoDB, so that's a multi-model database, so key value store documents and in particular graphs. So we have a Python client which talks to REST API using token-based authentication. Everything is in JSON, but we make use of MessagePack for transporting JSON in a more sort of optimized sort of binary form, because if you're sending sort of metrics or events at a very high frequency, just actually sending the messages can take a long time and slow things down. Then we're using Fast API to provide the REST API, and then it's obviously connected to the database, and there are a number of then microservices that do various things, for example, dealing with managing alerts or keeping track of heartbeats from each simulation run. So it's a graph database, so everything is stored in graphs. So for example, users can store their simulations or assign them to different folders, and then sort of as a way to sort of help people keep track of things. So this is an example from my testing. So there's a root folder and then lots of folders connected to that. And then each folder you can then obviously have associated simulation runs. So you might want to have like different projects in different folders, or different versions of things you're working on then inside of those folders. So you can do any sort of hierarchical thing you would like. And obviously everything else is also stored in graphs, in particular the simulation runs and files. So then if that makes it easy for the system to then determine dependencies between things. So for example, if you have a specific file which you eventually realize there's a problem with it or is wrong, whatever, you can then easily find out all other files and simulations that actually depend on that file. And then obviously we need to be able to store data as well. We obviously don't store data in the database. That data is stored in object storage using the S3 API. So that allows us to have the data being private but accessible from anywhere. So you can have jobs running on different HPC systems or some HPC systems and clouds, and it's possible for everything to get access to the data. So we make use of pre-signed URLs. So SimView generates the appropriate put or get pre-signed URLs. So that means that the data can then flow directly between the client and the storage system, so it doesn't have to sort of flow through any other system, so it's to get the best performance. Then one important thing is that we ensure that the SHA-256 checksums of all the files are unique so that data is deduplicated. So for example, if you have like a string of 3 different simulation or processing steps here, in this case there's sort of one run generates something here that's called file2.txt, then that's used as input to another simulation, then that writes file3.txt, and that's then used by another one. So in SimView you'd save the input and output files at each step, but internally it only keeps one copy of the file, which just obviously makes sense. So first of all, we'll talk about how SimView is used from within Python, because that's the simplest case, then move on to talking about from other codes. So it's just type pip install SimView to get access to it, and then there's a small configuration file which provides the URL of the server and an access token, and the UI provides an easy way of getting access to that. So then to use it, we then have to do initialization using the init method, where we can then specify a name if we want, or we can just use its default sort of randomly generated names. We can specify like metadata and any tags or other information. And then there's the sort of run.save step where it's saving the code itself. Then, for example, inside of the main loop of the application, you might then want to log metrics. where you just provide a dictionary with a list of the names and then the values. So in this case, there's just the run log._metrics. And this is just logging a metric that's called loss. And then you can, for example, if you have an error or something, you can then log an event. So that's just a sort of time-stamped message which you can then access or search for. And then finally, in this example, you can update metadata at the end if you want to and store any output files. So if you're using Python, it's quite straightforward to use. Obviously, if your code's written in other languages like Fortran or C++, you could consider, I guess, writing something that would then interrupt with SimView, but to begin with, we thought it would be simplest to have just a Python script which runs in parallel to the main application. So that, because if you're using a sort of simulation, the code that's been around for like 10 or 20 years, you don't necessarily want to have to start sort of fiddling with it. So this sort of more straightforward way of doing things. So if you can easily have the Python scripts read metadata, for example, if you need to from any of the files, you can then get the script to tail log files to extract any metrics or other sort of error messages, things like that. So as an example, so many codes write time-dependent values in log files. So this is an example here from OpenFOAM. So in this case, it writes out residuals and other stuff every sort of iteration, which helps people understand how well the code's how well it's converging or not, and you can easily extract these metrics and then send them into SimView. And then you can sort of watch things in real time rather than having to manually run scripts. So then once you've started adding data into the system, you can then look at it and search on the dashboard. This is sort of the current version, which will probably be replaced at some point, but so this is the main thing where it shows all the runs that you have, and you can search for things based on metadata or sort of other things. You can, the number of different statuses for things. So there are some here which are completed, there are some which are lost, which means they're probably like killed by a batch system or something. And then there are some at the bottom here called in the created state. So if you want to, you can, when you submit a job to a batch system, you can create a sort of stub run in SimView. And then when the job starts running in the batch system, you can then sort of reconnect to it. So you can also then sort of track simulations that aren't sort of running yet. And then in the alerts column, you'd notice that there's a couple which have a green tick and then the one that's red. So this is where someone has defined an alert rule. So the one which is green obviously means that everything is fine. The one that's red means that something must have gone wrong. And as briefly mentioned, so if you want to run, if you have one like simulation running on one system, then you want to run another simulation or processing script somewhere else that accesses the data that's from the first one, you can use SimView to also access that data. So here's an example where it says you specify a run name and you want the output data, we write it into a directory, and then we then start a new simulation using that as input. So it's sort of straightforward to access data. I think the next step will also look at directly being able to write like NumPy arrays and things like that, and then read them from the object storage as though it was just sort of slightly slow memory and not have to sort of use files as well. So now I'll go through a few example use cases just to show you how the system can be used. So I'll begin with a simple example where just sort of collecting metadata from, in this case it's a Fortran code. This is called process. So this is a Fusion Power Plant Systems code. So what this does is it assesses the engineering and economic viability of a nuclear fusion power plant. So it has quite simple models of everything involved with generating electricity from fusion, but they're sort of obviously very simple models, and what normally happens is people would start using this code, and then when they have something that looks reasonable, they'll then sort of run more detailed simulations for the different processes. But the starting point is sort of a code like this that's, for example. So in this case, we're sort of collecting lots of metrics. Some of them are shown here. So each row in the table here is a different simulation run. So in this case, like the first column here is showing a status. So we can see that some of the simulations, depending on the input parameters, they didn't converge. Some didn't, they just gave an error and completely failed. And so they generated no other metrics at all, no other metadata at all, and then the ones at the bottom which have the green in the converged, they actually work successfully. So with this, you can sort of keep track of all the different simulations and know sort of which worked and which didn't, and which sort of in the points in the parameter space didn't work. And then, for example, you can do like plots of the metadata if you want to. So the example here, it's just completely random, and it shows the high-grade heat output useful for electric production versus thermal to electric conversion efficiency. These are just two of the metadata values. I think one of them is the input to the simulation, and one is an output. And you can easily just make any plots you want, showing anything that you would find is useful. A sort of extension to that is in sort of a more advanced case where you're surveying parameter spaces. So in this case, we're looking at the impact of two parameters on the tritium breeding ratio. So,
and it's my own thing too. I own this, and I keep wrecking it, and it took down the projector, and now this pin is broken, but it'll still work with a little spark. It'll all come back, I promise.
Okay, I trust you.
You shouldn't. But you can't. It is going to come back. Yep.
It has, yes. Thank you. Okay, so so this is an example from work someone did, which was investigating the impact of two different parameters on the tritium breeding ratio. So just some background in a nuclear fusion reactor, tritium is one of the fuels that are needed, and what people want to do is to have a material inside the machine which produces tritium in the machine itself. So they don't have to have an external system that's creating or producing tritium. So you want to have to be able to work out the best way of producing this material to produce tritium. So in this case, we ran lots of simulations to run. There were all the input and output parameters were stored as just metadata, and in the plot here, each point just comes from the metadata from each simulation run. So it's just plotting the tritium breeding ratio, which is the thing that people are interested in, versus two of the different parameters. And so you can easily sort of do things like this and watch the progress in real time. So actually the person who was doing this work originally actually had, to monitor it, he'd set up a MongoDB database and a sort of plotting thing using an AWS function as a service type thing, and was making plots like this. But sort of with a system like this, anyone can easily do that and not have to set up infrastructure themselves. Then moving on to a sort of much more complicated case, where here we're looking at combining HPC and sort of AI machine learning. So obviously lots of people are running sort of physics simulations which take a long time to run, either sort of hours or even days. And people tend to need to run these lots of different input parameters. And obviously if the code takes a long time to run, that's sort of quite expensive. So what people are doing more and more these days is building surrogate models. So using machine learning to create a model which can produce an inexpensive approximation to the proper physics model, but it runs very quickly, so you can then use using less computing resources. And so an example here, sort of looking at the whole process of doing all the HPC simulations, and cleaning up data, and so doing the data generation step, then the data's getting cleaned up. So it's just putting it in the right format for doing the most simplest format for doing the training. We then produce a surrogate model, then that can be used for then doing the inference bit. And then obviously this process can be repeated as many times as needed. So in the data generation step, in this example, it involves running OpenFOAM, the CFD code, many times. And so here's an example of one of the pages in SimView. So this part shows all the input files, so you can just see that there are lots of input files that are stored in the system. You can then download them if you need them, or you can see what other simulations make use of the same input files, or even if these were generated by other simulations. And in this case, it's OpenFOAM, so monitoring the performance by looking at residuals is important. So here's an example plot that shows a time series plot showing the residuals as the simulation was running. So this is something you can just watch on the dashboard in real time, and you can see if things are sort of working or not. You don't have to run SSH into anything and run scripts. And obviously, if you've got lots of simulations running, you can do comparisons between different simulations, again, and watch things in real time. Then there's the cleanup step. So this is the step that just merges all the outputs from the previous steps, or the OpenFOAM simulations, and then this puts in a format ready for the machine learning. So you can sort of create graphs that sort of show what's happening. And the final step is then building the surrogate model. So this is just showing another page from the user interface. So you can see that it collects sort of basic information about the system, like the GPUs, CPUs, and things like that. In this case, there's lots of metadata specified, some of which we can see here. So that can be sort of numbers or just any type of plain text. And since this is machine learning and building a surrogate model, the metrics collected here is the loss during the training. So obviously we'd expect to see that to go towards 0. And again, you can sort of watch this from the dashboard in real time and compare different runs if you have sort of multiple things running simultaneously. And then in this case, once the surrogate model is created, the script also produced some plots that compare the surrogate model to the input. So you can obviously look at those in the dashboard as well. And just for people's, just if anyone's interested, this is creating a surrogate model for both a turbulent flow and a laminar flow across a two-dimensional cylinder. And so in these plots, the top plot is the simulation from OpenFOAM, and the bottom row in each sequence of plots is the surrogate model. So you can see that the agreement is quite good. And then obviously through SimView, you have a record of everything that happened. So I didn't want to show the graph that showed everything, because in this case I think there are 50 of each type of simulation running, so that would be quite complicated. But here it just shows 2 of them. So there's a data generation step. So there's the 2 codes which determine what parameters to use and run OpenFOAM. So there's these 2 codes. And then the OpenFOAM, so the sort of 2 things here that have lots of different input and output files. They are then used as inputs to the cleanup step, which then produced, the output files, which then go into the Python script that does the training for the surrogate model, and that produced the 2 PNG images and the trained model. So with SimView, that maintains digital threads, so you have a sort of record of all the different connections between everything, and you can see sort of exactly what's happened. And to summarize, so we've developed the proof of concept of a simulation monitoring framework that's sort of meant to be as generic as possible. It's not just for machine learning, but can be used with anything. The moment, so it's currently the proof of concept, but we thought it'd be useful to find out how many, if this is something that many people would want to have, and sort of what features they would need. And this system then provides a way of monitoring all your simulations from a single dashboard, keeping track of everything, storing data, metadata, and even having alerting, so you can see when simulations are failing. So at the moment, mainly what we're doing is looking at different number of use cases to understand sort of what we need to improve and what new features are needed for sort of everyone to be happy. Thank you.